All right. Hi, everyone. Welcome to the seminar. We are excited to have Abhin Shah today. Abhin is currently a final year PhD student in the EECS department at MIT, where he's advised by Devavrat Shah and Greg Warnell. He is a recipient of MIT's Jacobs Presidential Fellowship, and in the past, he has interned at Google Research and IBM Research. And before MIT, he graduated from IIT Bombay with a bachelor's degree in electrical engineering. And Alpine's research interests are in theoretical and applied aspects of trustworthy machine learning with a focus on causality and fairness. And today he will tell us about group fairness with uncertainty and sensitive attributes. It's all yours, Alpine.
Okay, thanks for the introduction. Thanks for the invitation. Hi, everyone. So I'm at MIT. This is my final year here. I'm on the job market next. And as mentioned, I work primarily on causal inference and algorithmic fairness. And today I'm going to talk about some ongoing work, which is in collaboration with folks at Florida, IBM Research, and MIT Watson AI Lab. This is a small audience, so feel free to interrupt me if you have questions at any point. I'll try to go slow in the beginning, maybe set the notation and setup, and then the talk will mostly comprise of two parts. In the first part, we'll try to focus more on a specific problem for Gaussian data and try to understand it from a geometric point of view, get some intuition. And then I'll give you a general algorithm and see how it applies in practice, okay? Okay, so with that, I'll get started. Let me start with a motivating example, and I'll keep coming back to this example throughout the talk. Suppose you want to build a machine learning model to predict, let's say, individuals' annual medical expenses. And to do so, you have a bunch of features such as age, location, BMI, number of children, and let's say whether the individual smokes or not. In addition to being accurate or precise, you also want your model to be fair, okay? And you want it to be fair with respect to some attribute, let's say gender in this example of the individual. And the question is, what does being fair mean? Well, it depends on how you're going to use your model's predictions downstream. And depending on that, you may want to focus on specific fairness criterion, okay? So let me just label things on the left as features, in the middle as sensitive attribute, and on the right as outcome. And an important distinction between fairness definitions, as we all know, is between group and individual fairness. And in this talk, I'll focus mainly on group fairness. And roughly speaking, group fairness compares quantities at a group level, typically identified by a sensitive attribute. For example, gender here, but it could also be age, race, and things like that. While individual fairness compares or cares about individuals being similar and how their outcomes compare or not. So there are three main group fairness criterion: independence, separation, and sufficiency. For independence, you may want your prediction of the outcome to be independent of sensitive attribute. For separation, you may want the same independency, but now conditioned on outcome. And for sufficiency, you want the independence between outcome and sensitive attribute, conditioned on prediction, okay? So far, I've just tried to set up one motivating example of this annual medical expenses with gender being sensitive attribute, which I'll use throughout the talk. And I'm just stating three well-known notions of group fairness: independence, separation, and sufficiency. In the first half, I'll focus primarily on independence, and then I'll show you how our results apply to separation as well, okay? So this is great, but while training your model, let's say in practice, this conditional independences are typically enforced through an optimization problem using two different kinds of losses. So you have one loss, which is the prediction loss, which measures the disagreement between what you're predicting with respect to the outcome. And then you have the fairness loss, which measures the degree of, let's say, group unfairness in this example. So the degree of violation of whatever conditional independency that you may care about, right? And your goal is to minimize the prediction loss such that the fairness is less than a predefined tolerance level, let's say epsilon. So you want to minimize or maximize your predictive power such that the amount of violation of fairness is constrained. So that's standard. And one point I want to make here, which will be used throughout, is that typically the sensitive attribute shows up in the calculation of the fairness loss. So even if you don't have sensitive attribute to calculate the prediction loss, you're mostly okay because you have other features to do that. But the fairness loss is defined with respect to sensitive attributes. So it's important to acknowledge that it shows up in how you calculate the fairness loss, okay? Okay, so let's keep that aside and let's look at the trade-off frontier for this insurance data set, which is standard benchmark, which is my motivating example again. So your goal is to predict the individual's annual medical expenses. This is a regression task. And you have sensitive attribute, which is gender, or for simplicity, let's say sex, and it's discrete. And I'm going to show you a plot where on the y-axis I have the mean squared error, which measures the prediction power, so lower is better. And on the x-axis, we have the fairness loss for the independence notion. It's not really important how I'm measuring this loss for now, but let's just say that this is the fairness loss measure when the fairness criterion is independence. And again, lower is better. So in a sense, you want to achieve a point as close to the origin as possible, okay? Um, okay, so here is a trade-off frontier. And let's say I'm obtaining this by fixing a particular architecture of my machine learning model. Again, I'm not interested in what's the best architecture or what happens when you change the architecture, including, let's say, the number of hidden layers, number of neurons, and so on and so forth. The point is, for a fixed network, you, let's say, try to obtain the frontier. And how do you obtain this? So you change the value of epsilon on the top right of my slide. And for different values, you get a plot like this. And let's try to understand this better. So suppose epsilon is very, very large. So what happens there is you don't really care about fairness that much, and all your attention is focusing on prediction. So you get a point on the right in some sense, okay? The rightmost points in some sense. So if you keep taking epsilon to infinity, you, and in some sense, converge to the points that I've shown here on the right extreme. Unfortunately, I can't really see where my cursor is, so I can't really point anything, but that's the point on the extreme right, let's say. On the other hand, if you, let's say, make epsilon super small, let's say if you take it close to zero, then you want your fairness, you're giving much more importance to fairness. So your fairness loss is going to be much smaller. And you're not paying that much attention to, let's say, prediction, and you lose some power there. So you get point on the leftmost here. And the reason why things don't really go to zero, because you only have finite samples in your data set. And you can, there is a certain minimum which you on, like on how minimum of a fairness you can achieve and how minimum of a prediction you can achieve. And that's why things on the X and Y axis don't really go close to zero. Okay. Okay. So this is so far so good. And yeah, again, this is for a fixed architecture. Throughout the talk, I'll just focus on, let's say, one particular architecture. It's not really important what the architecture is. But the point is, the focus is going to be what happens when you don't have sensitive attributes, or when there is uncertainty in sensitive attributes, and how worse are you compared to this frontier, how close can you get to this frontier, and those sort of things are what we are interested in, okay? By not changing the architecture. Of course, you can fix the same architecture, use it for all different methods, but that's besides the point here, okay? Any questions so far? Okay. Okay, so this brings me to uncertainty and sensitive attribute. So typically in the literature, it is assumed that you have access to the sensitive attribute of every individual or every sample in your training set. However, this is not actually true in practice. For example, you may have access to sensitive attributes for only a subset of your training samples. This is common for those data sets that originally did not collect sensitive attributes, but now you suddenly care about fairness for that data set. So you require to do some additional annotation. And there you may only, let's say, get sensitive attributes for a subsample or for subset of your samples. Another example is when your sensitive attributes are noisy or they have noise. So this could happen when sensitive attributes are collected, let's say, via a survey, and then participants fear of discrimination. So what they report may not be their true underlying gender or sensitive attribute value. Or you could, or like there are certain legal regulations and sensitive attributes released to public are often privatized due to, let's say, EU's GDPR or California's Consumer Privacy Act. So what's happening in this slide is there can be various sort of uncertainties, either due to missingness or noise or a combination of the two. And we want to see what you can do under this scenario. So just to be more precise, uh, this are some of the rows from the insurance data set. So you have the 5 features from before in the black, and then in the blue you have your outcome, the true medical expense that you want to predict or build a model to predict that. And you have your true sensitive attribute, which is gender. And what I'm showing here is, let's say, a few of the values are missing. So you may get something like this, okay? So there are question marks, and you don't have access to the green column. You only access to the orange column. Question is, what can you do then? And again, I want to emphasize, as I said previously, that the fairness loss is going to be computed using the orange column and not the green column. Of course, using, let's say, the black columns as well, but more importantly, using the orange and not the green one. Um, Alternatively, you could have noisy sensitive attributes. Let's say I'm collecting this gender via survey, and people, let's say, flip the value of gender with some probability which I have no access to. It may depend on their other features. So the missingness could be at random, could be not at random. We are not sure what the missingness pattern is. And you want to use the orange column to compute the fairness loss. Okay. Okay, so what I'm going to show you next is the frontier that you get, again, on the same data set as before, for the same task, for same sensitive attribute, everything seems before. And what I'm simply doing is I'm estimating the fairness loss using, let's say, uncertain sensitive attributes. And I'm going to show that it can lead to a model that does not accurately capture the target fairness levels. And the way I'm introducing uncertainty is in this data set of insurance, I'm just allowing my model to see some random 1% of sensitive attributes. And I'm hiding all other sensitive attributes. So I'm going to compute my fairness loss just using that 1% of the data. Okay. And once I do that, you get a plot. Yeah. So uncertainty is between missingness, and you get a plot like this. So again, you wanted to achieve a point towards the left bottom corner. The oracle has access to true sensitive attributes as I had before. And then there is this baseline method, which is which has access to a random 1%, and it provides a less control on the attainable values of fairness. So if you look at, let's say, the leftmost points, there is a gap between what you can achieve. Of course, you may ask whether this gap is significant or not, but in applications where, let's say, you really want to have you really want to have a certain fairness threshold, it may become significant. Or if you just change the x-axis to, let's say, percentages, then you see it's around 25% is what you're losing in terms of the attainable range of fairness. So this is indeed, in some sense, important to deal with. And this phenomena is, as expected, is repeated across other data sets as well. So let me move to adult data set, where, as we all know, the task is to predict individuals' income. So unlike insurance, this is a classification task, and sensitive attribute again is gender, which is again discrete. And again, I'm going to introduce uncertainty in the same way as before, just to see what happens. And you get a plot as before, and there is a gap in the amount of fairness that this different methods, or the baseline and the oracle, can achieve.
And I
Now, we have, yes.
in the previous plot, there was also a gap in the accuracy that you can achieve, right? And
Yes,
I
that is
wonder
right.
why there's also this gap in prediction accuracy. But in the next part, there is no gap, it's just fairness. There's just a gap for fairness.
Yes, 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 yes. Yeah, that's a great point. You're right. So as you can see, yeah, the lowest possible, let's say, mean square error is 0.09 here, but for the orange one, it becomes 0.015. So there is a gap, and as you correctly pointed out, over here there is not a gap. So I'm not really sure why this happens, but my educated guess would be that for adult you have a lot more samples to begin with, so and a lot more features to play with. So you have around 50,000 samples, and I guess like 30 or so features, if I remember correctly. For insurance, you have, I guess, only 5 features and I think 1,000 samples. So I'm not really sure why this is happening, but for our purposes, what's important, or the focus for us is just this, the level of fairness that you can achieve. Is there a way where you can, let's say, go to the extreme left? But of course, like you may ask what happens, let's say, if I have a random classifier. A random classifier will, let's say, achieve a fairness of 0, which is even better than the oracle here. But then the error rate for a binary classification task could be something like 0.5. So of course you want to achieve fairness, which is, let's say, lower, but not at that extreme cost of error or accuracy. So you want to remain in the same ballpark roughly, but try to achieve yeah, try to go as left as possible in some sense. So yeah, let me just move on for now, and we'll look at a different data set, which is the crime data set. So here the task is to predict the density of violent crimes in a locality, and it's also a regression task. The thing that is different than from before is your sensitive attribute is race. So for those who have worked with this data set, we know that sensitive attribute here is a continuous number between 0 and 1. So it's a bit different than what we have before. And so here we introduce uncertainty in a different way. We just add noise. So yeah, there is no way for us to, let's say, flip the value. So what we do is, so you want to add some noise and see what happens. So we could think of a way to flip the value because it's continuous. We just added a bunch of Gaussian noise independently. And as expected, we get a figure which looks like this. So yeah, so again, the focus is on the leftmost achievable points. And again, as I stated before, the epsilon that I had in the previous slides, the way I'm getting the leftmost points here is by making epsilon very close to 0. So I'm using values something like 10 power minus 3, and I don't really observe any change in the points I obtain when I move it from 10 power minus 3 a little bit on either side. So it's kind of saturates, and that's how I'm sort of confident that this is the leftmost achievable points. So that's really the focus, that can you reduce the gap between this blue lines in some sense, okay? So, okay, so all in all, the goal is to learn fair models despite uncertainty. And yeah, so this is, as mentioned, critical in applications where violating a fairness threshold can incur significant cost. And we want to go from this uncertainty to being fair and being precise or accurate. And so again, there is not like a mathematical objective or like definition of how better we are doing. So like what we want to do is we want to simply ask, can we reduce this gap in fairness? Okay, that's basically the question that we are going after in real world data sets. And you can frame it mathematically if you look at, I guess, so yeah, I mean, there's a way to frame it mathematically, and I'll tell you how to do it as well. But in real world, all we ask is, if we plot this frontiers, can you reduce the gap? And then depending on, let's say, what fairness thresholds a practitioner may care about, they can choose a particular uh, operating point on this curve, and see which of the methods they want to achieve. Okay, so I'll make this clear in a bit towards the end once I show some results. But for now, yeah, for now we just want to reduce the gap, and I'll give you an algorithm which is applicable to various settings, meaning classification regression, discrete continuous sensitive attributes both, and uncertainty due to missingness and noise, and also for notions of fairness of independence and separation. Okay, this is unlike most existing works, which focus on a subset of these different, let's say, settings. And I'll try to give you an overview of some of the existing work next. So there are three categories in which I've divided the works. So the first one is proxy variables. So several works have proposed methods to achieve fairness when you have proxy variables as substitutes for sensitive attributes. So for example, you can use zip code as a proxy with the effectiveness depending on the correlation between the sensitive attribute and the proxies. Um, and then there is this work out there by Jung et al. Where they propose a semi-supervised approach to impute sensitive attributes when they're partially observed, but they focus on classification tasks with discrete sensitive attributes only. Uh, we want to be a bit more general, and in fact, we can use their method as a pre-processing step for our method to convert uncertainty due to missingness to uncertainty due to noise because of by their imputation technique. But I'll not focus on that in the talk. And then the third line of work is about noisy sensitive attributes. Again, several works have been proposed to handle uh, noise in sensitive attributes with a focus on classification, discrete sensitive attribute, and by assuming a particular noise model where you know that the noise is independently flipped, let's say from 0 to 1 or 1 to 0 and so on and so forth with some fixed probability. What our method can do is our method can also work when the noise is not completely at random and it depends on, let's say, other features and so on and so forth. Okay. Okay, great. So in the remainder of the talk, I'm going to focus on a few things. Two parts. The first part will motivate our method, the empirical method that we'll propose using some theoretical insights by looking at Gaussian data and analyzing the problem of fair learning. Again, with the focus on independence notion of fairness. What we do is we reduce a specific instance of this problem to a quadratically constrained quadratic program. I'll show you how. When you have the true sensitive attributes, and then when you don't have the true sensitive attributes, we'll make this QCQP robust, okay, to ensure a strict fairness guarantee. And then I'll relax the robust QCQP and give you an intuition to how to generalize this beyond Gaussian data to get a general purpose algorithm. Um, and then I'll demonstrate the performance on various data sets as the three ones I mentioned before. Okay, so that's the next, I guess, 30 minutes or so. If you have any questions, please feel free to interrupt me again. Okay, with that, I'll try to set the formulation and notation. So you have, let's say, X, which is the input feature. Let's say three-dimensional. Standard notation, Y, you have the target or the outcome, and E is my sensitive attributes. I also have access to a predictor that I want to design a predictor in some sense, sorry, that accurately estimates the target variable for new input and also avoids discrimination based on sensitive attribute. And to achieve this goal, I have two like loss functions. So the first one is L, which is the disagreement between, let's say, target and my prediction, f of x and y. So L can be mean square error if you have regression, or it can be log loss if you have classification. So things are standard so far. I also have phi, which is a fairness measure, and it basically measures the level of discrimination of f. Okay, so the way you compute phi, it's a function of, let's say, my outcome, my sensitive attribute, and f of x. For example, if you care about independence, you want a sensitive attribute to be independent of prediction. So phi should be such that f of x is nearly independent of e. And then for other notions, you will choose an f such that independency is appropriately satisfied. Okay, so this epsilon basically measures the violation in the independency in some sense. I'll give you an example in the next slide as well. Okay. And capital F is a class of predictors. So let's say your neural networks. So you have some fixed set of networks. You want to choose one particular network, small f, such that this goal is satisfied. Okay. Okay, yeah, and yeah, I'll okay, so I'll jump to the Gaussian setup for now. So what I'm going to do is I'm going to model X, Y, and E as a joint Gaussian distribution. I'm going to focus on independence. So I want my prediction f of x to be independent of sensitive attribute E. And for these, let's just say things are zero mean. So let's not worry about the mean. Yeah, so let's say I want to, I'm going to choose my predictor f of x as the expected value of the outcome conditioned on u of x, where think of u of x as some representation of my features. So I have my features, I take some representation, condition on that, I look at the outcomes, and that's my prediction f of x. So let's look at like what I mean by that. So I have this graphical model over here. So I have x, y, and e, which have some joint correlation. I'm going to use x to construct u, and I'm going to use u to construct f in some sense. Okay, and that's basically what is happening here. And if you think about it, if you use the standard data processing inequality, if you ensure that u is independent of e, it will ensure that f of x is independent of e. Okay, so what I want to do is I want to construct a u such that it's independent of e. That will ensure that my prediction f of x is independent of e. That's my fairness criterion. And then after, let's say that is achieved, I'm going to make sure that my u or the resulting f is such that the prediction loss is minimized. Okay, so those are the two parts, moving parts here. Okay, and I'm going to measure the violation of independence by some divergence. So this is, I'm using a notation d bar. So this d bar divergence was proposed in 2019 in some work by Young et al. It came out of MIT as well. But the key point here is that this is some second order approximation of KL divergence. The exact form is not important here. What's important is that this measures some degree of violation of, let's say, independence between E and U. So I have the joint distribution P, E, comma U on the left, and I have the marginal PE multiplied by PU on the right. So the amount, so if they're independent, then two sides will be equal, and let's say D bar will be equal to 0. So I want to measure how bad the violation is, and that's my phi. I basically want to constrain phi to be smaller than some threshold epsilon. So if I take epsilon to be 0, that will ensure u of x is independent of e. Okay, makes sense? So,
Can I
so
ask a question before?
yes, please. Yes, please.
Can u be the identity function, like u of x equals x, or are you thinking of like a compression of all the features into one attribute?
It can be x as well. Yeah, it can certainly be x. Maybe that would have uh, helped make things easier. But the issue is then, like if you choose u of x to be x in my setup, then you want x to be independent of e, which you may or may not have because that's fixed, right? Like x and e are given to you. So if you choose your u of x to be x, I want to construct an f based on this u, right? So to get that independence, I'm just allowing a transformation such that the transform space, it's independent of the sensitivity.
Yeah, but that's one way of getting independence.
Yes. That's just, yeah, you're right. That's just one way which makes life much easier for this challenging problem for Gaussian, even for Gaussian data. So yeah, so I'll make 2 points. One is I'm choosing a particular measure of fairness, and things only work in my setup for a theory setup for that fairness, which is d bar divergence. Exact form is not important, but it's some approximation of KL divergence. It's also a divergence, by the way. And second is, as you said, this like my setup is specifically for use x to go to u of x, and then use u of x to go to f of x. You can do directly e to f of x, sorry, x to f of x without having to go via u. But we found that we can show some nice things in the setup, and there are some nice geometry that is involved, which some of you may like. So that's, yeah, great clarification question.
Thank you.
Okay, so with this choice of, let's say, phi, what we can show is this optimization problem is exactly equivalent to now maximizing, again, this d bar divergence between my the joint of y and u with respect to the margin of y and u, such that the corresponding fairness criterion is satisfied. Okay, so phi, the constraint is copied from above, but you can show that the minimizing this expectation becomes equivalent to maximizing the corresponding divergence. And it's a couple of lines proof, nothing fancy, but a nice observation. And the nice thing about this D bar, or the approximation of KL divergence, is you can now use the notion of canonical correlation matrices, or basically a normalized version of correlation between, let's say, U and V. So you have the covariance between, let's say, V and W are some of my variables over here. I look at their covariance and normalize them, and I call it, let's say, some B. So it's a normalized covariance or correlation matrix. And the nice thing about this divergence is that you can now, instead of working in divergence space, you can work in matrix space. So you can show that this problem becomes equivalent to finding a matrix A, uh, such that the inner product between A and this BYX, which is the correlation between Y and X, you want to maximize that such that this other inner product is smaller. So essentially, I'll explain you what's happening here. Let me actually go to the next slide. So yeah, so if you look at my graphical model, what's happening is this divergence is measuring, you want to go from, let's say, Y to U. So you want to basically, in some sense, capture BUX and BYX. And that inner product is what my objective is. So think of A as BUX. So I want to choose a U from X, which for Gaussian distribution with zero mean basically means I want to choose a covariance matrix or a correlation matrix, which is this BUX. Okay, so given X, I want to choose BUX such that the product of, in some sense, BUX and BYX is maximized, while the path from U to E is the product of that correlation is minimized. Okay, so again, you want to construct U such that it is maximally informative about Y, and you have to go through X. So you first go via this BUX or A, and then multiply it with BYX. But you also want to ensure that the product of, you also want to ensure independence between U and E, which is going from U to X to E, which is BUX and BEX. Okay, so what I've done is, starting with the general optimization, reduce it to divergence, and then reduce this to SDP, semi-definite program, or just dealing with matrices, if that makes sense. Okay, and what happens is this A becomes a matrix, which yeah, lies in this ball. Again, that the details are not important, but what's important is this graphical mapping of my optimization problem to this graph structure. Is it clear, or do you want me to go into more details?
I have one question. Where does L appear, the loss function appear in this transform?
Great. So what's happening is, again, so L is, think of L as the mean. Okay. So, so the loss function is going to be the expectation of y minus f of x whole square, because it's a regression task. So it's y minus the expected value of y given u of x whole square. And then you can show that minimizing that, the arg min of u is same as the arg max of u of this k, not kl, but this d bar divergence. So that the minimizer of the first objective is the maximizer of the second objective. And once you reach that, then you can also map it to a new problem, which is with matrices. Okay, great. Okay, hopefully things are a bit clear. And then now that we have this QCQP, things become super interesting. So let me go to the next slide. So what we show is that even though, let's say, your X is high dimensional, you only need to worry about two dimensions, because any optimal A star of this QCQP lies in the subspace spanned by BYX and BEX. So you can map any D-dimensional problem to a two-dimensional problem, which lies in the subspace. And let's look at the feasible space of A for this problem. Okay, so this is how let me use 2D dimensions. Let me use polar coordinates. So I have BEX, which is, let's say, some RE comma theta E point in this space. And I want to look at my feasible space, which is depends on the constraint. So I want to basically choose all my A's in this ball such that the inner product of A and BEX is less than square root epsilon. So I join BEX to the origin, draw perpendiculars at appropriate distances, and look at all points in between those perpendicular lines. And that's my feasible space. Great. Now, let's say someone also gives me the corresponding BYX. Okay, so let's say it's point RY comma theta Y. Now, how do I get my optimal A star? Well, what you want to do is you want to draw perpendiculars to this particular line from origin to BYX from the feasible space, and look at the maximum distance from the origin of the perpendicular point. Okay, so again, you want to basically maximize the inner product of a point with respect to BYX. So how do you do it? You join the origin to BYX, and the projection of that point is going to be the you draw to get the projection, drop the perpendicular, and then you look at the distance away from the origin of the point, intersecting point. And the one that gives you the maximum projection, that's going to be your A star. So intuitively, it will lie on the border. And for the particular BYX I have here, it's these two extreme points that I have here. Those things are symmetric here because it's squared. So like plus A and minus A is the same for me. So that's why I have 2 points here, but those are my optimal points that maximize the objective such that the constraint is satisfied. Okay, great. So far, we assumed that there was no uncertainty in sensitive attribute, which means given data, assuming it's Gaussian, I can compute its covariance, its correlation, meaning BEX, I knew it accurately, let's say. But in my example, or what I want to focus on is when I don't know BEX accurately. So I basically have a baseline, let's say, which estimates BEX using some data that I have. And let's say I call it B hat EX. And then I'm going to look at baseline method, which simply replaces BEX with B hat EX. This is similar to the baseline that I had before in my plots. And what happens is this baseline does not guarantee fairness. Why? Because let's look at BEX and B hat EX, and let's look at their corresponding feasible spaces. Now, as you can see, they are not necessarily overlapping. So if you choose a point which is in the feasible space of the second one, but not the first one, your constraint is not going to be satisfied. So that is when you are going to violate fairness. Okay. So if you choose your A or your optimal, let's say, representation U by using this yellow or orange feasible space, and when you go and deploy it in practice, you may get, let's say, kind of plots I showed earlier where the fairness was not able to achieve below a certain threshold. So that's really the intuition of what's happening here. Okay, great. Now I'm going to show you how to, let's say, design a robust QCQP for Gaussian data. And so I have this optimization problem, and I'm going to robustify this. I'm going to assume for now that I have an estimate B hat EX from data, but I also know that with high probability, my true BEX lies in some ball around this B hat EX of radius delta. Okay, so with high probability, my BEX lies in this point. Now, how to get this delta and how to get this ball is we have some results along those lines in the paper. But I guess what's important is to understand how to achieve a robustified version of this QCQP. So it's quite intuitive. What you do is if you have this uncertainty ball, you just ask that the constraint is satisfied for every point in the ball. That's one way to do it. If I know with high probability my true BEX lies in this ball, I ask my algorithm to achieve the constraint with respect to every point in this ball and then see what happens. Of course, you will lose on, let's say, the performance or the prediction, but you will get, let's say, strict fairness with probability 1 minus delta if the true one lies in this ball with that probability. So I'll show you some, okay, I'll make things a bit more concrete, but I want to stress that even for this problem with, let's say, infinitely many constraints, what we can show is that 2 dimensions is sufficient, meaning that and there will be an optimal A star of this optimization problem that will lie in the subspace spanned by BYX and B hat EX. Okay. Uh, okay. So with that, I'm going to show you. So this constraint has infinite. This optimization has infinite constraints. I'll give you a way to make it finite. So I'll give you a way to make it depend on only 3 points. So these 3 points are the ones that I've shown in the figure. So what we do is we relax the uncertainty space such that the feasible space is constrained. Okay, so there is some feasible space I'll get by having these infinite constraints, but I want to get some intuition on how do you do this beyond Gaussians. So I want to understand, can you do something similar by having finite constraints? To do that, I'm relaxing the uncertainty ball by a little bit, and I'm making the feasible region a bit smaller. And I'm going to see how much loss I get, things like that, and see how I can use that to go to non-Gaussian data. So again, it's not important how we obtain these points. If you want to understand more, you can look at the paper. But what's happening is we are reducing this QCQP with infinite constraints to one with 3 constraints by relaxing the uncertainty. Okay, and I'll show you how the feasible space looks like in the next slide. So this, let's say this. Okay, so in the orange circle, I have my uncertainty ball. I have my those 3 points in red, and the shaded region is how my uncertainty space is going to look like. Okay. Now, again, I don't know where my cursor is, but let's say my BEX coincided with B hat EX, then my true feasible space would be like imagine drawing 2 lines perpendicular to the x-axis, somewhere along where those 3 red lines are intersecting. And so you can see that I'm not going to lose a lot if my true BEX is going to be very close to my B hat EX. But if my uncertainty space becomes bigger and bigger, then I'm going to lose a lot and lot. My feasible space is going to be much smaller. So as you can imagine, like on the right-hand side, there is no point on the boundary of the circle. On the left-hand side, there were still points on the boundary of the circle. So under certain, depending on where my B uh, XY or BYX lies, on the left-hand side, I can still achieve, let's say, decent performance because I have some points on the boundary. On the right-hand side, I have no points on the boundary. So if my uncertainty space is bigger, you lose a lot. It's kind of intuitive. Um, I have one more slide before I go to the before I explain you how to go beyond Gaussian data. But I want to stress on this point that by doing this robustified version of Gaussian data, there are examples where you don't lose a lot in terms of prediction. Okay, so I'll show you a simulation in after the main algorithm, but I always want to let's stress the main point here. So what we do is we assume the uncertainty is because of, let's say, limited or missing sensitive attributes, and we whatever sensitive attributes you have, you use that to construct this ball. And let's say you keep on collecting more label sensitive attributes, then your uncertainty space will become better and better. So the orange ball will keep shrinking, the feasible space will keep on increasing, and at some point you will have enough, your feasible space will be large enough such that you can get the desired level of fairness without losing anything in terms of accuracy. Okay, so for example, let's imagine that your BYX is as I have on this slide in purple. Now try to draw perpendiculars to this particular line from my feasible space. Now, the point where this line is intersecting with the circle, that particular point has the largest amount of, let's say, projection, or that's my A star here. And no matter how much uncertainty I'm able to reduce, that A star will still remain the same point. Okay. So what I'm trying to say is if you have scenarios where the BYX and BEX are nearly independent, or your true Y and E are nearly independent, you get this free fairness in some sense. Okay. And that's what I mean by uncertain does not hurt. And we have other cases as well in the paper, but in the interest of time, I'll skip those. and I'll try to argue how we can use the idea from this Gaussian analysis to go to a general algorithm. So I only have a few more slides and a few more minutes as well. So I'll try to be quick here. So what you have is this. So we started with this particular optimization problem, but we did not have access to the green one, the green BEX. So we robustified it, and we lost something in terms of prediction, but we sort of ensured that the fairness holds. And one way to think of what we did is we took what the baseline did and we added multiple extra constraints. Okay. And so these two are equivalent because you can show that given B1, B2, B3, the first constraint becomes sort of redundant. But the point is, you can think of this algorithm as adding additional constraints to your optimization problem where you're using your data in some sense to obtain multiple estimates of b hat ex. So for Gaussian, you know that specific ones you need to ensure strict fairness are B1, B2, B3, which we have in our paper. But we can use this idea to, let's say, go to beyond, use this extra constraint idea to go beyond Gaussian as well. So let me try to argue how. So let's say I have access to all my sensitive attributes. So I want to do this optimization where the fairness loss depends on, let's say, the Oracle data set, which is same as the green one. But I don't have that kind of a luxury anymore. So what I want to do is I want to do what the baseline would do, that you constrain it using this uncertain set, but also add, let's say, this additional some number of constraints which depends on where the fairness is computed on, let's say, some subset, some such DIs. Okay, so that's the mapping on how you go from here to there. And now in the next slide, I'll give you one way on how you can construct, let's say, the sets DI. Of course, there are many ways in which you can do it. We don't have any theoretical guarantees on the way we propose, but we show that empirically it behaves pretty good. And so the question is, okay, so you have an optimization problem with constraints. So how do you solve this in practice? Well, typically people just take the Lagrangian dual and choose some Lagrangian parameter and then optimize over your, let's say, neural network parameters. But instead, what we want to do is we want to make sure that the Lagrangian dual does not play significant roles. We instead go and optimize over all lambdas as well. Okay, great. I'll try to argue how, I'll try to give you a way to choose this DIS. So what you have is you have this, let's say, limited or noisy uncertain set. And let's say we choose two parameters, some K, which is a subset of how many samples you have for sensitive attributes. And then S is the number of constraints. So we just draw uniformly with replacement multiple subsets from this uncertain set using, let's say, of size K, okay? So the idea that we, or the intuition that we get here is from Bootstrap, okay? And so that's really what's happening here. Okay, so I'll first tell you how, okay, so the baseline, it's constructing fairness laws using this D uncertain. We want to construct fairness laws using D uncertain, as well as, let's say, D1, D through DS, where these Ds are some subsets of size K from the uncertain set. So one could try and see how it behaves as a function of K and S. We only look at how it behaves as a function of S. We don't have any theoretical results, as I mentioned, but I'll try to convince you that this has some merit to it in practice, okay? Before we go ahead, any questions? One thing I would like to add is, again, like the intuition is that in some sense you are constructing a confidence interval around your uncertain set, D uncertain, by using this D1 to DS. And that's basically the intuition behind Bootstrap as well as behind what we are trying to do here. Okay, I think I have three more slides and all our simulations. So in the first one is synthetic Gaussian dataset. So this was the problem that we set out after. And here is the, so we're comparing with baseline where we replace BEX with B hat EX. We have our bootstrap methods with different values of S, let's say 3, 9, 27. And then we had this robust QCQP, which we know will ensure strict fairness because of how we are robustifying it. So here I'm showing you the number of violations of my fairness constraint with respect to the number of sensitive attributes. And on the right, I'm showing you the average mean square error. So as you can see, the robust QCQP is not losing a lot in terms of mean square error. Let's say beyond n equal to 300 in some sense. So it's sort of comparable. And this is a histogram on, let's say, so if I repeat the experiment, let's say multiple times, the frequency of violations of my fairness constraint for different methods is what I'm plotting here. So the dotted line is epsilon, which was 0.025. And I'm showing you that the baseline indeed violates this, let's say, quite often. Robust QCQP doesn't, but the orange one, Bootstrap S, it's somewhere in between, more closer to not violating. So just think of this. So this is what gives us some intuition that at least for Gaussian, this bootstrap method can be robust QCQP can be approximated by bootstrap S if S is sufficiently high. And now you want to understand how it behaves in practice. And we have more experiments in our paper on, let's say, different choices of Gaussian covariances, different kinds of uncertainty due to, let's say, missingness at random, not at random, different kinds of noise, so on and so forth, and see how robust QCQP and Bootstrap behaves and what happens. We also have many experiments on real data sets. I'll just show you three. So again, going back to insurance, we want to achieve better levels of fairness. And we are using chi-square divergence here, which is sort of standard these days, at least in group fairness notion. And this is the kind of performance that we get with S equals to 5. So as you can see, you wanted to achieve leftmost fairness points. And that is indeed what we are getting here. Of course, we are losing in terms of the performance a little bit because we are adding a lot more constraints, but we're able to achieve the desired fairness levels as was stated. Moving on to adult data set, here the amount of uh, loss in accuracy is less, but we are also not able to achieve, let's say, the levels of fairness close to Oracle. We are somewhere in between. As I mentioned at some point in one of the slides, that we can, let's say, augment our method by pre-processing step using, let's say, the method of Jung et al., where you can impute the missing sensitive attributes. And we observe that that gives a much, let's say, wider range of fairness levels. Um, in both of these plots, as I had before, the missingness was due to uncertainty. Sorry, the uncertainty was due to missingness. Now we also have due to noise in the crime data set. And again, we get similar performance here. In fact, we're doing better in terms of accuracy or performance than the baseline. But I guess the more important point is you're able to achieve the levels of fairness that the Oracle method is able to achieve. So we have set S equal to 5 in all the methods. And this results are just for independence. We get similar looking results for suppression, which you can find in the paper, which is available online. But I guess the key takeaway of what we're trying to do is we have a method which sort of is general and achieves this levels of fairness comparable to Oracle for different kinds of settings. And yeah, there are a lot of future work with respect to theory going beyond Gaussian, beyond independence, trying to understand Bootstrap is better with respect to fairness, performance, and computation, and so on and so forth. Yeah, but that's all I had. So sorry, I'm very close to the finish time here. But if you have any questions, happy to stay around.
Thank you. Thank you for the great talk. If there are any questions, feel free to unmute yourself and ask. I have one question.
Yeah.
So in the case of missing values for these sensitive attributes, one thing you can do is that you can look at the subset of the data where the sensitive attribute is not missing, and you can learn a mapping from the features to the sensitive attributes and use that mapping to predict the rest of the sensitive attributes. I wonder if
Yes.
this is something that you can compare your method to.
Yes, we indeed have. So we call it imputation method. I don't have the results in this particular talk, but I have it in the paper. And the point is, like, we are looking at a regime where you have sensitive attributes for only 1% of a data set. So let's say you train a classifier or a regressor to learn sensitive attribute first, and then let's say do the imputation. The behavior is not that great of that particular model. If you are at that extreme where you have only 1% of the data and you want to impute for 99% of the data.
Yeah,
But to give you an answer, it's quite similar to baseline in terms of what it can do.
I see.
Yeah.
Okay.
Yeah.
Thank you very much. And thanks for coming to our seminar.
Thank you. Thank you.
And I guess I see you all next week. Thanks.
Thank you.